Welcome to the Panda Protection Program, presented by the Team 6 members David Coenen, Christopher Dalisay, and Michael Lee. The World Panda Protection League is facing a critical challenge in securing the sensor network deployed in several large forest preserves in China, detecting the location of pandas and transmitting real-time information to a collection server. However, the network is vulnerable to exploitation by dangerous panda hunters, who intercept the incoming messages and exploit them to locate the pandas, posing a severe threat to their safety. This proposal aims to develop a robust security mechanism that can prevent unauthorized access, while providing secure transmissions of real-time information without compromising the network's functionality, accuracy, and reliability. The solution will be designed and implemented adhering to the low-powered hardware limitations capable of functioning unintended for long periods of time, incorporating modern encryption techniques with improvements to the signal mechanism.
Our employer has learned that another security company was hired to secure a similar sensor network for a different forest. Though details are limited as to what processes they used to secure the network, we do know that the hunters were still able to exploit it and locate the pandas. From what information we could obtain, we have concluded that the hunters were able to exploit the network by identifying patterns to the transmissions that uniquely identified which sensors were transmitting the data. They are able to listen in on the transmitted frequency, leading them to the origin of the signal and pinpoint the panda's location. The sensors were not rotating frequencies to obfuscate the transmission, which allowed them to intercept the entire message packet. The data was encrypted with the same symmetric key, allocating the same output with each encrypted packet, and there was no variation, allowing packet pattern detection.
On the left side of the screen, we were given information from the World Panda Protection League Q&A session. It was disclosed that no encryption is being utilized on the system today. Devices operate on low power constraints. Transmissions are conducted in short-range broadcasts with receivers in range. And the collection server sends time-synchronized messages. Hunters are not modifying or accessing contents of the sensor physically, and hunters are only interested in eavesdropping. Team 6 would like to propose a solution. First on the list, we'd like to discuss performing encryption and decryption on the data being relayed from the sensors to the collection server. Secondly, a solution of performing time-slotted narrowband spread spectrum frequency hopping that would provide transmission randomization.
Learning from the WPPL that the network traffic of the sensor data is unencrypted, we are looking to instill an encryption system utilizing the ARM-based software module that would sit between the sensor and the transmitter. The points we had touched on previously in regards to the system needing to adhere to a low-power setup requires us to utilize a lightweight encryption method. We went ahead and chose the lightweight block cipher present due to it being a well-known and exercised in the field, and it being both hardware and software efficient. There are a few points here on the slide that are reasons behind its lightweight nature, including a small 80-bit key, a 64-bit block size, and a 4-bit SBox, all of which reduce the need for power and have a much lower RAM usage than that of a full cipher like AES. We will be implementing symmetric encryption, utilizing a key set of 24 private keys that both the sensor modules and the collection server know about. Each key's usage will correlate to an hour on the 24 clock and will restart at the top of the list afterwards. The set of symmetric keys will be rotated by a park ranger or whomever checks the sensors as often as they're able. To keep the network encryption system live, the collection server will know of both the current key set being used and the new one being introduced so as to allow the rangers to update the keys on the sensor modules. The diagram on the right is a small-scale example of the collection server knowing the key sets 001 and 002, each containing 24 different private keys as a part of their sets, so as to allow the collection server to still be able to decrypt messages of the current and incoming new key sets. To address the issue of the other security company's unsuccessful encryption setup, we will be appending the date-time of when encryption took place to the tail end of the sensor message, so as to make the encrypted message look different for two of the same exact datasets. One of our theories as to why the other security group had failed was due to the fact that they had just used one private key, and encrypted each piece of data individually. Encrypting sensor 1, for example, will have a random output, but will always have the same random output since encryption is deterministic. The hunters would only need to create a data dictionary of the patterns they see, and know that the obfuscated data would always correlate to a certain sensor or panda. Our solution ensures the messages look unique and patterns cannot be detected. Note that the datetime being used as part of the encrypted message will be different from the timestamp, so as to not disclose any censored data or data types, but also to keep the encryption scheme decoupled from the censored received data, in case there are any changes to the censored data structure in the future. The datetime for encryption should also be set to a fixed size, so the decryption algorithm knows when the message ends. On this slide, we have our protocol narration, which depicts the flow of our encryption solution from start to finish. In step 2, after receiving the censored data in step 1, the sensor module will determine which private key to use based on the current datetime. In step 3, we perform the encryption mentioned in the last slide using said key. In step 4, the sensor sends the collection server the encrypted message, and both the datetime and the key set ID, so as to let the collection server know how to decrypt the message. These two pieces of information can be in plain text, since this data is purely for making the messages look random, much like a salt in a hash or a nonce. In step 5, the collection server determines which private key to use by the key set identifier and datetime passed. In step 6, the collection server decrypts the encrypted message with the corresponding private key. Knowing the fixed size of the appended datetime, the sensor data can be extracted. And in step 7, the message is stored. The assumptions on the left side of the slide depict what is known by the sensors and collection server.
We like to talk about the timesync protocol on the network. This is a known implemented feature confirmed by the WPPL that already exists from the previous architecture. We want to highlight how important this feature is. The time protocol keeps sensors synchronized with the collection server by broadcasting a UDP message, updating the sensor network. It is essential to protecting our proposed solution from potential time drift and providing constant synchronization, which is extremely important for timing of symmetric key usage, and our next proposal of frequency and channel rotation.
The time-based, time-slotted, narrowband, spread spectrum frequency hopping technique is an effective way to prevent the detection and interception of wireless signals. The main idea behind this technique is to make it difficult for unauthorized users to access the data being transmitted by constantly changing the frequency and timing of the wireless signal. The frequency hopping is synchronized between the sensor network and the collection server, which combined with the cryptographic protocol further enhances the security of the data transmission. The ARM device will periodically hop between different frequency channels in a randomized fashion, making it difficult for any potential attacker to intercept and decode the data. This is done by assigning each frequency range within the frequency band a unique channel and randomizing the frequency spacing between the channels. This makes it difficult for an attacker to predict the next frequency that will be used for data transmission, which in turn makes it highly improbable for an attacker to intercept and decipher the data being transmitted. To further enhance the security of our data transmission, we will incorporate a randomized time element into our system. This involves associating a randomized time interval with each time slot, adding an additional layer of security to our communication process. Each time slot is assigned to a random channel, and when the data is transmitted, it is sent through the randomized channel at the specified randomized time interval. By doing so, we can reduce the risks of jamming, interference, eavesdropping, and detection. This method makes it extremely difficult for an attacker to intercept or decode the transmitted data. The randomized time intervals and channels prevent any pattern recognition and make it virtually impossible for an attacker to predict the transmission timing and channel.
Thank you for joining us on this adventure to make a secure home for the pandas in our forest.